counting by complement is the very simple but sometimes very powerful idea that in order to count something, you instead count everything that is outside the set that you're required to count. So if I wanted to draw a picture, let's say I have this some universal set and I want to count the size of S, then instead of counting S, what I'll do is I'll count, I'll find the size of the universal set, and from this I will subtract the size of S complement, and that will give me the size of S. So instead of counting what is inside the set S, I count what is outside the set S, and then I subtract that from the total size of U. Now, why would you want to do that? Sometimes S complement is a smaller object than S, or it's easier to count than S. It has a little more structure, and so you can do it this way. Oftentimes, there are ways to not do counting by complement and do something directly, but it's a matter of convenience. So let me do a concrete example. Before we go to counting by complement, let me do something that has nothing to do with counting by complement. So this is just some combination stuff. And the question is, we are interested in number of strings, number of binary strings of length n with exactly k zeros. Okay, so I want to count how many ways are there to put zeros and ones of length n, so that exactly k of those are zeros. The trick is to try to interpret this using combinations or permutations, one of the two. So how would I do that? Well, what do I want? I want, if I think of there being n blank spaces, then I want to put 0 in k of those blank spaces. So another way of interpreting it, this question is saying number of ways of choosing k spots in a list of n blank spaces. So I choose some k spots, and then in those spots exactly I put zeros, and everywhere else I put 1, and that will give me a binary string of length 1. And now, as it suggests in the wording, I'm choosing k spots out of n, and so the answer is directly n choose k. Okay, nothing to do with complement so far, but I know that number of binary strings of length n with exactly k zeros is n choose k. Great. So suppose now I change the question slightly, and I'll make it a little more concrete. I want number of binary strings of, let's say, length 4 with at most 3 zeros. Okay, so now what I've changed, instead of exactly 3 zeros, I have at the most 3 zeros. Then this changes the problem completely. Let me start by trying to solve this directly. Now I know how to do it when I have exactly k zeros, but now I want at most 3. Now what does at most 3 mean? Well, I can have either no 0, or I can have 1 0, or I can have 2 0, or I can have 3 zeros. So a binary string of length 4 can have one of these 4 options, in which case it will be at most 3. So I can break this up as number of binary strings with no zeros plus with 1 0 plus with 2 zeros and plus with 3 zeros. And why I'm adding? Because a binary string can either have 0 zeros, or it can have 1 0 or 2 0. So these 3 options are ours. These 4 options are ours. You can't have a string which has 0 zeros and 1 zeros. And now I'm looking with exactly 0 0. So this should be 4 choose 0 with exactly 1 0. So that is 4 choose 1, 4 choose 2, 4 choose 3, and that is my answer. So number of binary strings with at most 3 zeros is number of binary strings with either 0 zeros or 1 0 or 2 0 or 3 0, and hence this number. Okay, so that's one way of doing this problem. But there is another way of doing the same problem, and that is using the complement. So let me copy the problem. Okay. So now what I'll do is I'll try to find what are the strings for which this fails. So what is the opposite of at most 3? At least 3 or more than 3. So the opposite of this is number of binary strings of length 4 with more than 3. How can a string of length 4 have more than 3 zeros? If it has to be all 4 of them are 0. So in this case, you see that more than 3 actually is just saying equal to 4. So now I'm asking how many binary strings are there of length 4 with 4 zeros? Well, there's exactly one. Just all 4 zeros. There is no other option. Now I'll focus on the universal set. The universal set is number of binary strings of length 4 with no restriction. So number of binary strings of length 4 with no restriction is 2 to the 4. Why is it 2 to the 4? Well, I have 4 blank spots, and in the first spot I can have either 1, I can have either 0 or either 1. Same here, and same here. So for each spot I have 2 options, and then I'm making 4 choices. So there are 2 times 2 times 2 times 2. That's 4. So this is number of binary strings of length 4. This is all the binary strings of length 4. Then 1 is the number of binary strings with more than 3 zeros. And so from these two, I can conclude that the number of binary strings with length at the most 3 is 2 to the 4 minus 1. Just to see that the two extremely different answers are in fact exactly the same, let's actually simplify out these numbers and see what we get. This is 16 minus 1, that is 15. So I'm getting 15 strings. And if I try to expand this out, I will get 1 plus, I'll just do this in my head, 4 plus 6 plus 4. If you want, you can do this more systematically. And this, as you can see, is also 15. So you get the same answer, but which two things that look very different and use very different methods. Now, why was counting by complement like slightly more compact in this case? Because the opposite of at most 3 was easier. But that's not always the case. Like the problem could easily have been at least 3, and in which case maybe the answer to do the original problem is easier than the complement problem. Okay, so this is usually a judgment call. You see a problem and you look at its complement and decide by yourself which one is the easier one to compute, and you compute that one. Oftentimes, both are computable. So making the wrong decision doesn't affect you too much. It just means you might spend a little more time doing those calculations.